Now, boundary condition. You have to know only that, and once you remember that, it's easy. Boundary condition. Let's go one at a time. If you ever meet a fixed end you know is defined as an end in which the beam has no rotation and no deflection. No deflection implies in the conjugate beam no bending moment. That's how the conjugate relations are, right? These two go together, these two go together, these two go together. So if you say delta is 0, then in the conjugate beam you're saying M is 0. If you say theta is 0, then you're saying shear force is 0. This S should be written as V. Okay, some people use, in my book I used S as the notation for shear force for a reason. V suggests it's vertical, but a beam can be inclined. So, when will you get a situation which will guarantee that always your bending moment can have a non-zero value? Can have. It's like your bank account. It could be 0 also. No, bending moment will always be 0 and shear force will always be 0. This will happen only in a free end. Always in a free end, unless you apply a concentrated moment or shear force here, which will never happen in the conjugate beam, because the loading on the conjugate beam is your curvature diagram. There are no concentrated loads ever going to act. So this is satisfied. So it's very easy to remember. Fixed end becomes free. Free end similarly becomes fixed. Because these two quantities have to be non-zero. That means you should always have a non-zero bending moment and shear force guaranteed when you have a fixed end. So the fixed end becomes free, free end becomes fixed. Ulta. Very easy to remember. What happens to a hinged or roller support? Well, in a hinged or roller support, deflection is free, is 0. That means bending moment is 0. And rotation is non-zero. That's why it's free to rotate, which means shear force is non-zero. That will always be satisfied in the same hinged or roller support. So, in a real beam, if you have a hinged or roller support, keep it like that in the conjugate beam. No need to change anything. If you have an intermediate support in a continuous beam like a two-span beam, here it cannot deflect, or deflection is 0, which means in the conjugate beam moment is 0. Moment is 0 is guaranteed only if you have an internal hinge, right? Similarly, if this is going to have a slope, generally a non-zero slope. That means shear force should not be 0. Here also shear force. Remember the child parent example, some shear is transmitted from the child to the parent. So remember, when you have an intermediate support in a continuous beam or a beam with an overhang, the replacement is an internal hinge. And if you have an internal hinge, it becomes a intermediate support in your. That's all. If you remember this, you can crack any problem. What does it mean? Real beam, if it's a cantilever, the conjugate beam is a reverse cantilever. Fixed end A becomes free, free end B becomes fixed. Simply supported beam remains simply supported beam. Propped cantilever with an internal hinge, well, the fixed end becomes free, the prop remains a prop, and the internal hinge is replaced by an intermediate support where this is continuous. Mind you, luckily for you, all these still remain statically determinate, totally determinate. So it's easy to calculate. And here's the funniest of the lot. Fixed beam. The conjugate beam is free beam. Then you'll say, how will this structure stand? Well, luckily for you, it has to only stand in your imagination. But real structures also like this. The aeroplane, for example, the helicopter, they're able to stand. But they are self-equilibrated, right? So don't break your head too much about this. This is all your imagination. This is reality. Good. Now, it's good to know some properties of your curvature diagram. You see, curvature diagram is given by bending moment diagram divided by EI. Bending moment diagram can have any funny shape. So you should quickly be able to find the total area and the centroid. For a rectangular, very clear, if the height is phi, it's constant, then the area is phi into L and the centroid is bang in the middle. If it's triangular, area is simple, it's half that of an equivalent rectangle and the centroid is located at a distance 1/3 to 2/3. This centroid, this is all common sense, we know that. If it's not a right angle triangle, but a triangle which is like this, then also the area remains the same, but then you need to know the formulas to locate. It's very easy to remember. Let's say this vertex divides the span in the ratio AB. Then the distance from the left end is given by A plus L the whole by 3 and the distance from the right end is B plus L the whole by 3. You can derive these formulas. If you have a trapezium, then the area is obviously average height into length. And there are formulas to get the centroid if you need them. You can always do something clever. You can divide this into two parts, rectangle whose centroid you know, triangle whose centroid you know. But you can also use. This is important. If you have a parabola like this is a typical bending moment diagram you get in a cantilever AB subject to a UDL. And if you divide the bending moment diagram by EI, you get a curvature diagram. You will find that the area of this parabola with a zero slope at B is always going to be 1/3 the area of the equivalent rectangle. So rectangle has an area of phi into L, 1/3 of that is the area of this parabola, provided the slope here is 0. If the slope is not 0, there will be a small error. And the centroid divides this in the ratio 1:3. So the centroid will be L by 4 from here and this will be 3L by 4. Remember? Sometimes you have a parabola of this kind, that is actually the other half of this. So clearly the area of this will be 2/3 of the rectangle. And this centroid divides this line in the ratio 3:5. Remember that. Again, we are assuming that the slope here is 0. I think that's enough. With that, we can crack most problems. Let's look at applications. Let's take this first problem. Okay. Now, this problem most students will find difficult to do if given in the exam. And you do any method. Except direct integration method, other methods will be tricky for you. So, I want you to try this. Problem. Okay, continue. So, let's say this beam is subject to temperature gradient like the kind we gave in the first problem. Okay, minus T plus T. In practice, you get such things, for example, when you are sitting in an air-conditioned room, or the reverse, when it's cool outside and hot inside. Whatever it is, we are assuming a linear strain gradient, and this will make the beam curl up. Actually, it will deflect, and let's say it deflects like this. This can also come from differential shrinkage because the point cannot lift up. You can prove, and we've done this before, that the strains are alpha T. Alpha is the coefficient of thermal expansion, and the curvature is alpha T divided by D by 2, where D is the total depth. Now the question is very simple. Tell me what is the maximum deflection and what's the maximum slope. Do it using conjugate beam method or moment area method or any method you know. So what do? Well, the curvature diagram is given to you, right? What will you do? You have to draw the conjugate beam. The conjugate beam is also simply supported. It's subjected to the loading on the conjugate beam is nothing but the curvature variation. The curvature diagram is the loading on the conjugate beam. and you know that the total area of the load, total load, imaginary load is phi into L. The load is acting upward. Why? Because the curvature is positive. You remember Q by definition pointing upwards is positive. So the reaction should point downwards. And what are these two reactions, by the way? These two reactions are a measure of the shear force. And what does the shear force mean? Shear force is nothing but the slope. So your first answer you've got, the maximum slope is given by the shear force in the maximum, the reaction in the conjugate beam, it is phi L by 2, very easy. And phi, by the way, is alpha T divided by D by 2. And we know that the maximum deflection is at the midspan. So in the conjugate beam, we take a free body at the midspan. And you can see that there is no shear here, which proves that the slope in the middle is 0. But there will be a bending moment here, and that bending moment will be the deflection in your real beam. That's how you do it. Okay. And you can calculate that. You know the bending moment in a simply supported beam subject to UDL is QL by QL squared by 8. But you can use the same thing here and you get the same answer. Instead of Q, you put 5. That's all. You cracked it, you got the answer. In the previous problem, there was no bending moment. Now we'll do the same problem with n moments. But now I want you to not only give me the maximum bending moment and rotation, I want you to also give me the equation for delta and theta at any location x. This is given to you. I'll start you off and you finish. This is my conjugate beam. On the conjugate beam, I put my curvature diagram, positive. Okay. Now I give you 2 minutes to give me an expression for delta and theta. That's a break. I'll come back in 2 minutes. Give me the answer. Okay. Okay. So first find the support reaction. Support reaction is total load by 2. Whatever reaction you get, now I've put a tilde sign showing that this is a conjugate beam. It's not the real beam. Right? The real beam here does not have a shear force. So that's this left hand side is the real beam, right hand side is the conjugate beam. The reaction here is going to be your slope here. So it's simply m naught L by 2EI. Then you take a free body of your conjugate beam, cut any section x and find out expressions for shear force and bending moment. Whatever expression you get for shear force will be an expression for the slope in your conjugate beam. Whatever expression you get for bending moment in your conjugate beam, sagging positive, will be the actual expression for your deflection in this way. You will find that deflection will always come negative because by definition, deflection pointing upward above the x-axis is positive. So why don't we do this? You have this free body, this distributed loading you know, so you can write expressions. The centroid of this area will be exactly in the middle at x by 2. So it's very easy to write this expression for shear force in your conjugate beam, which is nothing but the slope in your real beam is given by this. And you can draw a diagram. And this diagram is easy to understand because if in a real beam, if you had a UDL, the shear force varies like this, except that the signs are reversed. Your Q would have been minus, your shear force here would have been plus, here it would have been minus. That's the only change. What about your rotation, your deflection? Find out the bending moment in the conjugate beam. You get an expression like that and your deflection variation is given by that. And this is the bending moment diagram that you would get if you had a uniformly distributed load. So it makes sense. And if you want the maximum values, well, you've already got the maximum slope, theta max, and the maximum deflection you will get by substituting in this expression x equal to L by 2. You get m naught L squared by 8ti. We got the same solution in the previous example. Remember, only thing there, the curvature was given to you straight away. Now, bending moment is given to you. You're converting bending moment into curvature by dividing it by EI. So sometimes when conjugate beam method is taught, people don't even mention curvature. They simply say M by EI diagram. That's a bad way to understand, because in a real problem you may have no M at all. You may have only curvature. M by EI is nothing but curvature. And remember, we've assumed the beam to be prismatic. So you can also deal with non-prismatic problems, and we'll take a look at that. So now let us see what happens if you had a concentrated load in the prismatic beam. And we don't want to derive the expression. Practicing engineers don't want to waste their time. Just we want to know the maximum deflection and the slope. Maximum deflection, remember the formula, PLQ by 48 EI. We are now here to prove it. How to prove it? This is your real beam. The question is, derive an expression for delta max and theta max using the conjugate beam method. First, draw the bending moment diagram. We know how to draw it. Find the support reactions. Draw the bending moment diagram. Please note, our interest is not the bending moment diagram. The question is, I'm interested in the deflected shape. There will be another bending moment diagram in my conjugate beam, that you don't get confused. This is useful to get my loading in my conjugate beam. My conjugate beam will also be simply supported. Remember, that support condition doesn't change. So in my conjugate beam, simply supported beam, I have this distribution of loading, which is nothing but the same bending moment diagram divided by EI. So the maximum value will be at the midspan, and this ordinate divided by EI. So I've got a triangular shaped loading, distributed loading in my imaginary conjugate beam, and if I cut the section anywhere, the shear force in this conjugate beam will give me the slope at the same location. The bending moment in the conjugate beam will give me the deflection at that point. But I don't want to do all that hard work. Question is very clear. I want to know only the maximum deflection. I know the location of that. That's going to be bang in the middle, under the load in this case, at x equal to L by 2. So, and support reaction is very easy to get, because the reaction here will give me theta max. What's the reaction here? Well, total load divided by 2, symmetry. So what's the total load? Look at the sign convention. Here the bending moment is positive. So the loading Q in my equivalent conjugate beam must also point upward. That's positive. So there is a sign convention here. But even if you don't know the sign convention, or you don't care for the sign convention, you know actually how your theta and delta are going to look. So don't worry too much about this. What's your total load? Well, that's the area of this triangle. Area of the triangle is half the span into the altitude. So it's very easy to get, PL squared by 8. Half of this will come here, half will come there. And straight away you got the first answer, theta max, which is theta A, theta B, is PL squared by 16. One answer you got. Now we want to find delta max. What do? You have to cut a section. Either you take left half or right half in your conjugate beam. Let's take the left half. So we are now drawing a free body of the conjugate beam. In this free body, you already have calculated the support reaction and it's pointing downwards, PL square by 16 EI. You got this load is 1/2 of the triangle, and whatever you get here, you'll know that this must be also equal to this because half the load. That's why there's no shear here. No shear here means the slope here is 0. But there is a moment here, and that moment is the deflection. Very easy to get. That moment in your conjugate beam at the midspan is a deflection. So how do you get the moment? Well, first you get the resultant force acting here. That's the area of this triangle, which is equal to this. But you know that the centroid of a triangle is located at 1/3 the distance from the this side. So if this is L by 2, 1/3 of L by 2 is L by 6. So it's very clear. This moment is this load into L by 2 minus this load into L by 6. By the way, the load itself is the same. So actually it's this load into 2L by 6. Straight away. PL cube by 48 EI. You will get a minus sign strictly, but then you are interested in modulus, the absolute value. That's so we proved that formula which we assumed in the earlier stages of today's session. Good. Similarly, you can do, please try these two problems. Okay, now we are doing cantilever beams. Two cantilever beams are there. Here I have a concentrated moment. First let me ask you a question. And I have a concentrated load. This will certainly go down. This, will it go down or will it go up? I want to chat with you. So tell me, will this beam go up or down? And so you have to answer up or down. Okay. So let's see. Up or down? I wish we could have a dialogue, because if you give one of the answers, I'll say why. Since we have some time, maybe first whoever is giving the answer must come with a mic. Then I'd like to have a discussion. Downward. So I want you to be near the mic, GCT, and tell me why downward, why not up? Why downward, why not up? Interview question, admission for MTech or MS at IIT Madras, or job interview. Your answer is correct, but it could have been a guess. But guess is also good if it's a correct guess. But why? The deflection is going to be downward. Your guess is correct for a very simple reason. You will find that to satisfy equilibrium, the moment at A must also be anti-clockwise M. So you know from that, the direction of moments itself, that beam is going to hog. If that beam has to go up in single curvature, it's going to sag. Very simple. The only way hogging can be done is in this manner, just as when you apply the constant load here. So your answer is correct. I wish you gave this answer. If you do it the other way, first of all, intuitively you should know it will come down because you know how the couple is going to act. But even if you made a mistake, you'll find if it goes up, it's going to sag. And moments like this can't achieve sagging. You have to have it the other way. So you must get a good feel of this. So this is our bending moment diagram. And the conjugate beam for a cantilever is a reverse cantilever. The fixed end becomes free, the free end becomes fixed. On this, you're going to put your curvature diagram, which is the same as your bending moment diagram, divided by EI. Okay? Please pay attention. This is an imaginary diagram. And if you get the support reactions, the total load on that beam is half the area, so m naught L by EI. The support reaction there is the same load m naught L by EI, and that must be your slope, your largest slope at the free end. And the moment you get there is the deflection m naught L squared by 2 EI. That's it. That's your deflection. How long does it take you to solve this problem? If you're very good, 1 minute. 1 minute. It will take you much longer by the conventional direct integration method or by the moment area method that they continue to teach in colleges. So simple, so enjoyable, so brilliant. So you saw how this was done. Do the same thing for this case where you have a concentrated load. What's the shape of your BMD? It's a triangle. Now don't draw a triangle with zero value at A and maximum at B. That's not how it works. The reflected shape is similar and it will be like this. It's a hogging moment. So on your, what's your conjugate beam? It's going to be like that. So the only difference between these two is here the loading is triangular, here it's constant, uniform. And all you need to know are the reactions at this imaginary fixed support in your conjugate beam. Total load is half the area, half PL by EI into L, and its CG, its centroid is located at 2/3 this distance. It's very easy to calculate. Your maximum slope is the reaction you get or the shear you get here. That's PL squared by 2 EI, and the moment is PL cubed by 3I. It's very easy to derive, and so you don't have to mug up anything. You've got a strong weapon in the conjugate beam method. Easily you can solve simple problems.